Thank you everyone for coming to this seminar. So today we are honored to have Professor Neil Gong from Duke University. So Neil is an assistant professor at the ECE department at Duke, with also affiliation with CS department there. So his research interests are cybersecurity, privacy, and related machine learning problems. He received several awards, including NSF Career Award, Army Research Young Investigator Award, and Facebook Research Award, IBM Faculty Research Award, and several Best Paper Awards. So Neil received a BE degree from the University of Science and Technology in China with the highest honor, and a PhD in computer science from UC Berkeley. So let's welcome Professor Gong.
Okay, thanks, Jeff, for the introduction and for inviting me to give this talk. So hello, everyone. Welcome to my presentation. So my talk is about robust content moderation for generative AI. So before I discuss the research, I'd like to first acknowledge my students and collaborators in this research. So as you know, generative AI empowers many new applications, such as AI-powered search, art creation, writing assistant, and even scientific discovery. However, generative AI also raises many ethical concerns, such as the generation of harmful content and boosting disinformation and propaganda campaigns. Content moderation aims to address these ethical concerns of generative AI. And generally speaking, content moderation tries to do two things. First, preventing the generation of harmful content, which is usually implemented using safety filters, and detecting AI-generated content. And recently, different countries have new AI regulations, and those new AI regulations actually have explicitly mentioned this content moderation. For example, this is the EU AI Act, which explicitly mentions preventing the generation of illegal content and disclosing that the content was generated by AI. This is related to detecting AI-generated content. And in US, in last October, the White House issued an executive order, and watermarking AI-generated content was listed as a key technology, okay, which is basically used to detect AI-generated content. So in this talk, I will discuss the robustness of search content moderation in adversarial settings. And in particular, I will focus on AI-generated images. But some of the results and the techniques can also be generalized to AI-generated text, videos, or even audio. This is a node map of this talk. In part one, I will discuss our work on how to evaluate the robustness of watermark-based detection of AI-generated content. And in part two, I will discuss how to evaluate the robustness of safety field-based prevention of the generation of harmful content. So let's look at part one first. Detecting AI-generated content, roughly speaking, has two approaches. One is called passive detection, and the other is called watermark-based detection. The key idea of passive detection is to leverage artifacts in AI-generated content. So basically, you can imagine you extract artifacts or features from AI-generated content and human-generated content, and then you can build a classifier. It's basically a binary classifier. right? And then you can use that binary classifier to detect AI-generated content or human-generated content. However, the challenge for this passive detection is that it has high false positives and false negatives, even if there are no attacks at all. Okay. For example, OpenAI actually released a passive AI-generated text detector. But after some time, OpenAI abandoned that passive detector because of its high false positives and high false negatives. On the other hand, watermark-based detection has recently been widely deployed by industry, such as Google, Microsoft, OpenAI, and Stability AI. And that is the focus of this talk. So before I discuss how to evaluate the robustness of watermarking-based detection, I'd like to first introduce some technical background about image watermark. So an image watermarking method consists of 3 key components. These 3 components are watermark, encoder, and a decoder. A watermark is a bit string. So basically now, suppose we are given an image and a watermark. The encoder takes the watermark and the image as an input and outputs a watermarked image. And the watermarked image looks very the same as the original image. And given any image, the decoder decodes a watermark. If this image has a watermark like this embedded, then the decoded watermark will be very similar to the watermark that we embedded into the image. So roughly speaking, watermarking methods can be classified into 2 categories: long-learning based and learning based. In long-learning based watermarking methods, the encoder and the decoder are usually handcrafted based on some heuristics. And these long-learning based watermarking methods have been studied for many years, more than 2 decades. And it is commonly believed that these long-learning based watermarking methods are not even robust to common post-processing, such as JPEG compression, Gaussian noise, Gaussian blur, brightness contrast, and so on. For example, if you take a picture, you embed a watermark into that image, into that picture, and you transmit on the internet. And during transmission on the internet, maybe JPEG compression will be used, right, to compress the size of the image, right, to reduce the communication cost. And after that JPEG compression, the watermark disappears. For example, Stable Diffusion actually uses a long-learning based watermark to embed watermarks generated by Stable Diffusion. Okay? And we did some simple experiments. We basically use Stable Diffusion to generate a watermarked image, and then we do JPEG compression. As you can see, this JPEG compressed image looks very the same as a watermarked image, but the watermark has been removed. So Stable Diffusion won't be able to detect this image as watermarked image anymore. So the second category of watermarking methods is called learning-based. And in this method, encoder and decoder are neural networks, and they are automatically learned using deep learning techniques. And these learning-based methods were believed to be quite robust against post-processing because they can leverage adversarial training. And I will discuss adversarial training next. So now let's suppose we have an original image, and suppose we randomly sample a watermark and use an encoder to embed the watermark. Okay. So we have this watermarked image. And then we use a decoder to decode the watermark from this watermarked image. So this decoded watermark should be similar, right, to the watermark we embedded into this image. So in standard training, we basically collect a lot of images, and we jointly train the encoder and the decoder such that the decoded watermark is similar to the original watermark for all those images, for all those training images. Okay? So that's how we train the encoder and decoder in standard training. In adversarial training, we add another layer called post-processing layer between the encoder and decoder. So now the idea is, now we have this original image, we randomly sample watermark, encode it into the image, but then I post-process the image. For example, I do JPEG compression, I add Gaussian noise, I do whatever post-process to this image. And then I decode, I use a decoder to decode the watermark from the post-processed image. And I still want the decoded watermark to be similar to the watermark we embedded into the image. Okay. And then we jointly train the encoder and decoder. Okay. So if we do this adversarial training, the decoder can still decode the watermark we embedded into an image, even if the watermarked image has been post-processed. So that's a little bit background about how watermarking method works. Next, I will describe how we can use watermarking to detect AI-generated content. During generation, let's suppose a generative AI model receives some prompt and generates an image. And before releasing the image, we are going to embed a watermark. And we call this watermark ground truth watermark. We embed this watermark into this image, and then release the watermarked image. Okay. And then during detection, let's say we are given an image. We first use a decoder to decode a watermark from it. And then given the ground truth watermark, we can compute the bitwise accuracy between the two watermarks. The bitwise accuracy is basically the fraction of bits that match in these two watermarks. And then if the bitwise accuracy is larger than a threshold tau, we detect that this image is AI generated. Otherwise, we see this image is non-AI generated. Okay. So as you can see from this detection method, only the decoder and the watermark, the ground truth watermark, are needed during detection. And then the key challenge of watermark-based detection is how to set the threshold tau. And the key idea to set the detection threshold tau is to pick a value such that we achieve a desired false positive rate. Let me explain a little bit more details. Suppose we have an...
No, I have a quick question about the detection algorithm. So we actually know the watermark, the ground truth watermark in real application?
That's a very good question. During detection, we do need to know the ground truth watermark. So you can imagine, actually, I will discuss this a little bit, how this detector can be deployed in real world. For now, let's assume, let's say OpenAI deploys the model. Whenever OpenAI generates an image, OpenAI embeds the watermark. And later, when you do detection, you have to send that image back to OpenAI. And then the OpenAI tells you whether it's generated by its model or not.
Okay.
So OpenAI knows the ground truth watermark. Yes.
But if the image was not generated by OpenAI, that means they don't have the ground truth, right?
Exactly. If that image was generated by Google, then OpenAI will detect it's not AI generated. But actually, more specifically, it's not generated by its own model.
Okay. Thank you.
Okay. So now let's say we are given a non-AI generated image. We can also use a decoder to decode a watermark. And we have the ground truth watermark. and we can calculate the bitwise accuracy, right? Remember, the detection is based on this bitwise accuracy. So the key idea is that if the ground truth watermark is picked uniformly at random, okay, then this bitwise accuracy actually follows a binomial distribution, right? Because each bit matches with probability 0.5. So the bitwise accuracy follows a binomial distribution. For example, this curve shows an example distribution of the bitwise accuracy. And given this detection threshold tau, the area of this shaded region is basically the false positive rate. The false positive rate is a probability that you falsely detect an non-AI generated image as AI generated. Okay. Then, for example, if we want to make the false positive rate smaller than 10 to the power of -4, and the watermark length is 30 bit, then the tau should be at least 0.83. So that's how we can set the threshold. And in the previous detector, we basically, the detector is basically a single tail detector. We also proposed a double tail detector, which detects an image as AI generated if the bitwise accuracy is larger than tau or smaller than 1 minus tau. And we show that this double tail detector is more robust than the single tail detector. Okay. So next, I will describe how a detector can be deployed in practice. There are many different ways. For example, one way is to deploy a detector as detection as a service. In this case, the provider of the Gen AI service also provides detection as a service. For example, OpenAI deploys the watermarking and also deploys the detector. Okay. So anyone can send an image to OpenAI, and OpenAI tells you whether that image was generated by its model or not. In end-user detection, the detector can be deployed as an end-user app, for example, mobile app or browser plugin. Okay. So every user can install the app, and whenever the user sees an image, can use that app to check whether the image is AI generated. In public detection, the decoder and the ground truth watermark are publicly released, so everyone can do the detection. Okay, and in this case, the individuals can even personalize the detection threshold tau, depending on their desired false positive rate. And in third-party detection, the Gen AI service provider shares its decoder and ground truth watermark with some selected third parties. For example, Google has already deployed watermarking AI-generated images. Maybe Google can share its decoder and ground truth watermark with Twitter. So Twitter can detect, right, can detect the images generated by Google's AI model that are propagating on Twitter. Okay. So those are some background about how watermarking method works and how watermark-based detection works. And then I can discuss how to evaluate the robustness of such watermark-based detector. So in our work, we consider the following threat model. In a white box setting, we assume the attacker has access to the decoder. Okay, but the attacker does not have access to the encoder, does not need access to the ground truth watermark. And the attacker aims to evade detector with any threshold tau bigger than 0.5. Okay. So first of all, the tau has to be larger than 0.5. Okay. So basically, in the white box setting, if the attacker generates an AI generated image, and that is watermarked, the attacker basically wants to add a perturbation to that image, okay, such that whatever detector people use, okay, whatever detection threshold people use, those detectors can't detect this perturbed image as AI generated. And in the black box setting, we assume the attacker has access to the API of a specific detector. For example, if OpenAI deploys its detector as a service. So OpenAI exposes some API for people to use. Then the attacker has access to that API. So basically, the attacker can send an image to the API, and the API returns yes or no. Okay. And in this case, the attacker aims to evade this specific detector. Okay. But the attacker does not know what detection threshold this detector uses. Okay. And in our work, we focus on watermark removal. So basically, you have a watermark image, we want to add perturbation to remove the watermark. And some works also study watermark forging or spoofing, which basically means that if I have a non-watermarked image, I want to perturb this image such that the detector detects that the watermark is in that image. Okay. But technically speaking, the watermark forging and spoofing is actually the same as watermark removal. So we are going to focus on watermark removal. Before I discuss any technical details, I'd like to give you one visualization example. I first show you results when using standard training to train the watermarking encoder and decoder. So this is the original image, okay? AI generated without watermark. And this is the watermarked image. Okay? It looks very the same. And these 4 images are post-processed by common post-processing methods to remove the watermarks. Okay? As you can see, some post-processing methods actually already sacrifice the image quality when removing the watermark. But JPEG is still good, right? JPEG can remove the watermark without sacrificing the image quality. And the last 2 columns corresponds to the images generated by our method in the white box setting and the black box setting. Okay. They look very the same as a watermarked image, but now the watermark has been removed. And the next row shows the results when we use adversarial training to train the watermarking encoder and decoder. Now, as you can see, the common post-processing substantially sacrifice the image quality when removing the watermark. But our method can still generate images that are very the same as a watermarked image when removing the watermark. Okay. So from these results, we can see adversarial training is quite robust to common post-processing, but not robust to our strategic advanced post-processing method. So in the white box setting, suppose we're given a watermarked image, IW. Our goal is to add a minimal perturbation delta to IW, such that each bit of the decoded watermark flips. And formally, we can formulate finding such minimal perturbation as this optimization problem. So the object function basically measures the magnitude of the perturbation. Here we use L infinity norm, but in general, we can also use other ways to quantify the magnitude of the perturbation. And the D is a decoder. And this symbol means flipping each bit of the decoded watermark. Okay, so we basically, given a watermarked image IW, we can solve this optimization problem to find the perturbation. But it's hard to solve the optimization problem exactly, so we can use some approximate algorithms. Theoretically, we can guarantee that once we find the perturbation by solving this optimization problem, we can evade single tail detector. However, the perturbed image, IW plus delta, can still be detected by a double tail detector. Why? Because the decoded watermark is flipped. Every bit is flipped. So the bitwise accuracy becomes too small. So originally, if we don't add a perturbation delta, the decoded watermark is very similar to the ground truth watermark, right? We detect it's AI generated. But now I add a perturbation, every bit of the decoded watermark flips, so the bitwise accuracy becomes so small, and it's still detected by the double tail detector. So to address this challenge, we design another method to find the perturbation. And our intuition is that long watermarked images have bitwise accuracy around 0.5. Okay? So basically, if you randomly sample a long watermarked image, you use a decoder to decode the watermark from it, and then the bitwise accuracy between the decoded watermark and the ground truth watermark is around 0.5. Okay. Therefore, we add minimum perturbation to a watermarked image to make its bitwise accuracy close to 0.5, such that the perturbed watermarked image is statistically indistinguishable with long watermarked ones in terms of their bitwise accuracy. So formally, we find the perturbation by solving this optimization. So again, the object function is to find a perturbation with minimal error infinity norm. And this constraint basically means after we add perturbation to the watermarked image, the decoded watermark has a bitwise accuracy around 0.5. And this epsilon, this small epsilon, is used to quantify the difference between the bitwise accuracy and 0.5. So as you can see from this optimization problem, W is a ground truth watermark. So if the attacker has access to the ground truth watermark W, the attacker can solve this optimization problem to find the perturbation delta. But recall, in our threat model, we assume the attacker does not know the ground truth watermark W. So this constraint is actually not applicable. And to solve this challenge, we came up with another constraint, okay, which is an approximation of this constraint. Here, WT is some random watermark, okay, picked by an attacker, and let's call it target watermark. Okay. So the idea is the attacker wants to find the perturbation delta. And after adding the perturbation delta to a watermarked image, the decoded watermark is going to be similar, is going to be very similar to a random watermark WT. Okay, so if the decoded watermark is very similar to a random watermark WT, that basically means the decoded watermark is probably going to have bitwise accuracy around 0.5 compared to the ground truth watermark. Okay. So we can solve this optimization problem using some gradient descent-based method, of course, approximately solving it. And we did some theoretical evaluation on the success of our attack. We define evasion rate as a probability that a perturbed watermarked image is falsely detected as long AI generated. And we use evasion rate to evaluate the success of our post-processing method. And for single tail detector, we can derive a lower bound of the evasion rate as follows. Here, tau is a detection threshold. So recall that our method does not need the information of tau. So basically, whenever you give me a watermarked image, I use my method to find the perturbation delta, and then I add that perturbation to this watermarked image, and then this basically shows if a detector use the detection threshold tau, then this is a lower bound of my evasion rate. And this, for double tail detector, we can also derive a lower bound of evasion rate as this. So this we can actually do some simulation to verify that this attack is very successful. And this graph shows some empirical results. The x-axis is a detection threshold tau, and the y-axis is the evasion rate. And the different curves correspond to different image data sets and our theoretical lower bound. Okay. So as you can see, the evasion rates are nearly 1 when the detection threshold tau is larger than around 0.75. And note that the detection threshold tau has to be larger than some value, right? Has to be actually larger than this value at least, in order to achieve a small false positive rate. So in other words, in practice, if we want to make watermark-based detector achieve a very small false positive rate, then that detector is going to be very non-robust to our method. Okay. So that's like a fundamental trade-off, right, between the false positive rate and the robustness. And this graph compares our method with those common post-processing methods in terms of the perturbations that add to watermarked image. So again, the x-axis is the detection threshold tau, and the y-axis is the average perturbation that different methods add to watermarked image. And the different curves corresponds to different methods. Okay. And this curve is our method. Okay. So note that for common post-processing methods, we set their parameters such that they achieve the same evasion rate as our method. So as you can see, when these methods achieve the same evasion rate, our method adds much smaller perturbations to the watermarked images, and thus better maintains the visual quality of the images. And so in this figure, the x-axis is the detection threshold tau, and the y-axis is the evasion rate, and these two curves correspond to standard training and adversarial training. So as we can see, our method achieves almost the same evasion rate no matter the encoder and decoder are trained using standard training or adversarial training. This is because our attack actually does not depend on how the encoder and decoder are trained. In this figure, the x-axis is the detection threshold tau, and the y-axis is the average perturbation. And as we can see, when adversarial training is used, our attack adds larger perturbation. This basically means adversarial training does improve robustness, but it's probably not enough, because even if we apply adversarial training, the perturbation is still small. So some takeaway messages so far. So learning-based watermark-based detection has good robustness to common post-processing in non-adversarial settings. But it's completely broken in the white box setting, in adversarial settings. And adversarial training improves robustness, but still is insufficient. So next, I will quickly go through the black box setting. So recall that in the black box setting,
I have a small question here. So the decoder is supposed to output just binary strings, right?
Yes.
So that means the operation formulation you wrote down there, obviously the constraint is not differentiable. It's actually not continuous, right? So how people actually handle that?
This
yes.
one?
Yeah, because the decoder you have to discretize things into binary strings, right?
Right.
So
yeah, that's a very good question. So first of all, I think there are definitely many opportunities for people in optimization. So what we do is very naive. Okay, I would describe it naive, straightforward method. So what we do, we translate this constraint into some object function, like come up with some loss function. Say this, we want this decoded watermark and this watermark to be close. So we form a loss function, like square, like L2 long, just compute this. Yeah, these two bit string, we just compute their difference, L2 distance, for example, into the object function. So we minimize, we found the perturbation such that these two are close. And but during the search process, we check this condition, whether this condition is satisfied.
I see. Okay.
During calculating the gradient, we don't consider this constraint. Yeah.
Okay.
But again, it's very approximate algorithm, and we don't even know any theoretical guarantee of this approximation algorithm. So I think there should have many opportunities for optimization researchers. Yes.
But do you think it matters if we don't solve this problem exactly? I mean, the thing is that do we worry about actually finding the minimal delta here?
That's a very good question. So see, in our experiment, we find even if we approximately solve it, empirically the attack is still successful.
Right. I believe so. You know, the thing is this. Okay, so if we make delta very large, obviously we can easily change things. But the thing is,
right. But
you know, I think from OpenAI point of view, you know, the thing is that or whoever deploy this, you know, you kind of want to make sure that the probability is small, right? Because you know, if it's too significant, then people can either detect that, right?
Yes.
And there's a countermeasure there.
Yeah, it is. To me, I think it's meaningful. It's meaningful because you basically, if we can really find the minimal delta, that basically tells us something about the robustness of a watermark, right?
Right.
If you can show, the minimal perturbation has to be larger than 10, that probably is pretty good. My watermarking method is pretty good, right? Because if we say, I have this watermark method, if you want to attack me, you have to add a perturbation that is at least this value. And that value is not very small. Is right? It's quite good. That actually tells us some robustness.
Yeah.
Tells us robustness.
Yeah, yes. I think people may probably naturally just try cross interpret or approximate the difference because you're comparing two binary streams, right?
Yes.
But
yes.
Simply would blow up the values because you want to make sure the difference is greater than, you know, on the order of 1, right? 1 minus epsilon. But cross interpret will blow up the values. So, you know, I think particularly this is actually very tricky.
Yes, I agree with you. I think our students also tried the cross entropy. They tried the different loss functions to measure the two bits.
This, right? And they're totally changing the scaling, right?
Yes. Yeah. Okay. Yeah, that's very good discussion.
Now, can I also ask a question related to the concept?
Sure.
So, yeah. So suppose the image, or in general, the artistic work is generated by machine first, but then polished by a human. Then shall we still, or to what extent of delta here, should we still claim this as machine generated? So we can well define the problem.
I see your point. So what you are saying is if the delta is large enough, maybe that is not AI generated anymore.
Yeah, I feel this is kind of beyond the
technical question.
Probably, yeah, not a technical question, right?
Right.
So in the research, usually how should we set the range of delta for the study of the robustness issue?
Yeah, that's a very good question. So I think how to set the delta, I would say the delta. So I would say the delta, once we add the delta such that the two images really looks the same.
Okay.
Then that's probably the threshold we set the delta. But still, that's not that's harder to quantify technically. We may need some
I feel image probably is a reasonable solution,
right.
But for text, it's a bit trickier because we can just always paraphrase the same sentence.
Yes, for text, it's trickier. Yes, I agree. Yeah, I think for this question, maybe I don't know. It's more like a societal issue. Everyone in the world, we may agree on something. See.
Yeah. This question puzzled me for a while because I also work a lot on watermarking these days and didn't have Yeah,
that's a very, very critical question. Yes.
Thank you.
Okay, let's move on to the black box part. So in the black box setting, the attacker has access to the API of the detector. So the detector is basically a binary classifier. So every classifier is characterized by its classification boundary. Okay. Let's say here, I just use an example. This is the boundary, the classification boundary of the detector. Okay. And this side belongs to AI generative. And this side belongs to non-AI generative. Okay. And now the attacker has a watermarked image. Now in the black box setting, we basically start from some initial perturbed image. And this initial perturbed image is detected as non-AI generated. Okay? Maybe this initial perturbed image just some random noise. Okay? It doesn't look really the same as a watermarked image. But now the idea is we interact with the API. Okay? Via interact with the API based on the returned result, AI generated or non-AI generated, we adjust the initial perturbed image. We move it towards the watermarked image to reduce the perturbation, to make the perturbed image similar to the watermarked image. Okay, so this is something that may happen. Okay, let me play it again. So we start from the perturbed image, we interact with the API, and then adjust. Maybe this time I move this image to be close to that boundary, but still on the other side. Okay, I move the image to be closer to the boundary, but it's still on the non-AI generative side. And then I do this again, repeatedly do it again, until I repeat this process until I use all the query budget. Okay, the query budget is basically the maximum number of queries we can issue to the detection API. Okay. So theoretically, the evasion rate of this attack in the black box setting is guaranteed to be 1, because during that search process, we always guarantee the perturbed image is detected as non-AI generated. And in this graph, the x-axis is the detection threshold time, and the y-axis is the average perturbation we add to the watermarked images. And as you can see, the perturbation still is quite small. Okay. Although it increases as the detection threshold time decreases. And this figure also shows that adversarial training improves the robustness, but may not be sufficient. Okay. So the x-axis is the query budget, and the y-axis is the average perturbation. And this curve corresponds to adversarial training, and this curve corresponds to standard training. So basically, given the same query budget, if adversarial training is used, we need to add a larger perturbation to the watermarked image to evade the detector. Okay. So to summarize a little bit for the watermark part, so the industry probably shouldn't publicly release the decoder. So we cannot perform white box attack. Actually, this is what exactly Google does. Okay. And adversarial training can improve robustness and should be used, but probably is still insufficient. For example, in the black box setting, we may dozens to hundreds of queries can still evade a detector while maintaining the image quality. Okay. But maybe we can use some stronger adversarial training, which we are still exploring now. And to improve robustness, maybe the generative AI service can restrict access to the detector API, so the attacker can't even access the detector API. But in this case, attacker can't perform the black box attack, but the attacker may be able to perform some other attack, like transfer attack. Okay. So that's part 1. Next, let's go to part 2. Fortunately, the part 2 will be much shorter than part 1. Okay. So part 2 is about robustness of safety filter-based prevention of harmful content generation. Let me first introduce a little bit of background about safety filters. So in the context of text-to-image models, there are 3 categories of safety filters. The first category is text-based. So now here you have a prompt. The prompt goes through a text encoder. And then we have a text-based safety filter. This text-based safety filter may take the text embedding or the prompt itself as input and then decide whether it's sensitive or not. If it's sensitive, then we won't output any image. If it's not sensitive, we use a diffusion model to generate an image. In image-based safety filter, we go through the normal process of generating an image. And then for the outputted image, okay, we do some safety filter based detection. Okay. So basically, for example, you can imagine this is basically an image-based classifier. So you generate an image, this image-based safety filter basically detects whether this image is sensitive or not. And in text image-based safety filter, we consider both the prompt and the image to do filtering. Okay. For example, we have some text embeddings of sensitive concepts, some predefined sensitive concepts. Okay. And then when we generate an image, we also generate an image embedding for the generated images. And then we compare the image embedding and the predefined sensitive concept text embedding. If the image embedding is close to some predefined sensitive concept text embedding, then that image is sensitive and we won't show that image. Okay. Actually, Stable Diffusion uses a text image-based safety filter. Okay. So our work basically aims to generate some adversarial prompt. So suppose, let me introduce adversarial prompt a little bit. So now given a target prompt, PT, this target prompt PT would generate a not safe for work image if we send it to the text to image model and the safety filter is not used. Okay. But when the safety filter is deployed, this target prompt PT will be blocked. So the model won't generate a sensitive image. So our adversarial prompt PA is basically a variant of the target prompt PT that bypass the safety filter and can still generate an image that has the same semantics as the image that the target prompt PT would generate. So here MPA is the image generated by using the prompt PA, and MPT is the image that would be generated by using the target prompt PT if the safety filter is not used. Okay. So that is some definition of adversarial prompt. And our goal is basically to generate such adversarial prompt to bypass the safety filters. So in our threat model, we assume we have a text to image model that is deployed as a cloud service. And we call this model target model. And the attacker's goal is to generate an adversarial prompt. And the attacker has access to a text encoder locally. And we call this text encoder shadow text encoder. And the attacker can query its shadow text encoder without any constraint. But the attacker can only issue a limited number of queries to the target model. This is because the target model usually charges users based on the number of queries they send to the model. For example, OpenAI, okay, DAO-E2, right, charges users based on the number of queries they send to DAO-E2 API. So before I show you how our method works, I'd like to show you an example first. And in this example, we assume the target model is DAO-E2. And we assume we have an image-based safety filter. And here, instead of showing you really disturbing images, I assume cat is a sensitive concept. Okay, we want to deploy this image-based safety filter such that DAO-E2 will not generate cat images. Okay, and we basically design this image-based safety filter ourselves and append it to DAO-E2. And now, if I send this prompt to this target model, I couldn't resist petting the adorable little cat, then I won't receive any image because it's sensitive, it's blocked by the safety filter. But now using our method, using our method, we can replace this cat as another token, glucose. And then we will bypass the safety filter and still generate a cat image. Okay. So as you can see, actually here, this is a watermark embedded by dial E2. So this image is indeed generated by dial E2. Okay. So now let's describe a little bit high-level idea about how we find such adversarial prompt. Suppose we have a target model, okay, which is deployed as a cloud service. And we have a target prompt PT. I couldn't resist petting the adorable little cat. Okay. First of all, in this target prompt PT, I can rank the tokens based on their sensitivity. Okay. So in this example, for example, I know cat is the most sensitive token. Okay, based on the image based on the safety filter. And our key idea is to use reinforcement learning. In particular, we use a policy network to model the distribution of the tokens that we should replace cat with. Okay, so let me repeat this. So now this is my target prompt, and I know cat is a sensitive token. I want to replace cat as some other tokens. Okay, but what other tokens I should pick? I should replace with. I use a policy network to model a distribution over all the possible tokens. So I have a token vocabulary. I use a policy network. This policy network models a distribution over all those tokens. And when I replace cat, I sample a token from that distribution. Okay, so basically I sample a token from that distribution. For example, this time I sample dog from that distribution and replace cat as dog. And then I get this adversarial prompt for this iteration. Then I send this adversarial prompt PA to the target model. And then the target model will return some results to me. These results include whether the safety filter is bypassed or not. If it is bypassed, the generated image is also returned. Okay. Then based on the results, I assign some reward. In particular, if the safety filter is not bypassed, I assign some negative reward. And if it is bypassed, then I assign this similarity between the embedding of the generated image and the embedding of the target prompt PT as a reward. Okay, and then given the reward, I will update the policy network. So I update the distribution over the tokens, and then I repeat this process. Okay, until I find an adversarial prompt such that the safety filter is bypassed and the generated image has sufficiently large similarity with the target prompt PT. So in our evaluation, we consider 200 target prompts, and the evaluation metric is bypass rate. Bypass rate is basically the fraction of prompts that bypass the safety filter. And we also use FID score between the generated images and the real not safe for work images. So FID score basically measures a semantic similarity to some extent, the semantic similarity between two sets of images. And if the FID score is smaller, it means the generated images better maintains the not safe for work semantics. So let's first see some results for stable diffusions, open source safety filter. So if I just use the original target prompt, the bypass rate is 37%, which means the stable diffusion safety filter is not too bad, right? It can detect 73% of the target prompt. But then we use our method to perturb this target prompt to get the adversarial prompt, and then the bypass rate of the adversarial prompt becomes 100%. And the FID score of the of the generated images is around 132. So if I just tell you 132, it may not be that meaningful. But I can give you a baseline. So the FID score for the target prompt generated images is around 113. So this is basically we remove the safety filter of stable diffusion and use a target prompt to generate some images and calculate the FID score. So as you can see, these two FID scores are close, okay, which basically means our generated images maintain the not safe for work semantics. And the average number of queries is around 10. And we also did experiments on dial-E's closed source safety filter. We don't know. So first of all, dial-E2 has deployed safety filters, but we don't know how their safety filters are implemented. Okay, so we just treat it as a black box. And this table shows some results. And so these are some existing works. We basically extend some existing work to bypass the safety filters, and none of them works well. Okay. And our method substantially outperforms existing methods when extending them to bypass safety filters. So to summarize a little bit, we basically showed that existing safety filters are not robust to adversarial prompts. Attacker can basically jailbreak text-to-image models to generate disturbing images using a small number of queries. Okay. So in this talk, we basically described how to evaluate the robustness of watermark-based detection of AI-generated content and how to evaluate the robustness of safety filter-based prevention of harmful content generation. So that concludes my presentation. And let's see whether we have more questions.
Thank you so much, Neil, for your excellent presentation. Now it's the time for Q&A. Feel free to raise your question in the text box or just speak.
Yeah, I have a question. So in your example, like when you attack the image, you have evaluated using a single attack method, like impose a JPEG compression or use a Gaussian filter. So have you tried to like test whether the model is robust to a combination of multiple attacks at the same time?
That's a good question. First of all, we haven't tried. We haven't tried doing JPEG compression and then Gaussian noise simultaneously. But I would imagine, but I may be wrong, okay? I would imagine the learning-based watermarking method may still have quite good robustness against those combined common post-processing. It's because of adversarial training. So you can, for example, you can also do such combined post-processing during adversarial training. So remember, in adversarial training, we have a post-processing layer, right, between encoder and decoder. So in that post-processing layer, you can do such combined post-processing during adversarial training. So if we do that type of adversarial training, the watermarking would be robust or would have good robustness against those combined post-processing. That's my guess, okay? But we haven't verified it. Yeah, that's a good question.
Yeah, I'm concerned in that because the adversarial setting, you must have a very strong prior, like what are the common attack or corruptions that can be imposed on the image. In the real world setting, the attack may be entangled. You may have multiple or complex attack, and which are not that common. So
yeah, I think you are right. So what I think what you mentioned is basically means when we design defense, we should consider such kind of combined attacks, right?
Yes.
Yeah. That's a very good point. Yes.
Also, in the adversarial setting, you have like you are trying to minimize the the visual, I would say like you minimize the infinite norm of the delta, which means the difference of the image and the original image and the new image you construct.
Right.
Like there are definitely a trade-off. Like if you are making this too small, like I don't think the new generative image would be robust to do some like if you perturb the lowest bit of your pixel values or other transformations that may not be robust. But if you set this too higher, your new generative image may have some like artifact that can be visually visible to the humans. So how do you like how do you think of this trade-off? Like what is the more practical way people deploy this?
Okay, very good. Let me rephrase your question a little bit. So the question is basically about the delta, right? If we add, so we add a small delta, we add a delta to a watermarked image to get a perturbed image. If the delta is too large, then the perturbed image has some weird artifacts, right? It won't look very the same as a watermarked image anymore. Okay, so if that's the case, if we can only design an attack, okay, let's say I have a watermarking method, and you come up with a very strong attack. But even if you come up with a very strong attack to find that delta, to find that perturbation, your perturbed image still has weird artifacts. Then that means your attack is not successful. That means my watermarking method is actually quite robust, at least against your attack. So when designing an attack, to evaluate the robustness of the watermarking method, we aim to find the perturbation that is as small as enough, such that we add a perturbation to the watermarked image. There is no weird artifact. They look weird is the same, but still the watermark is removed. You won't detect the watermark anymore. So that attack is a successful attack. And on the other hand, this type of watermarking method is not robust. But if we can, actually that very relates to our goal of designing robust watermark, right? So our goal is to basically design a robust watermarking method such that whatever attack you use, ideally, okay, whatever strong attack you use, if you want to remove my watermark, you have to add a large perturbation such that you introduce artifacts. If we can design such a watermark, that's great, right? That's very good. That's excellent. That is our goal. That is our goal of designing robust watermarks. Yes.
Yeah, thank you.
So you talk about the black box attack. Do you know what are the state-of-the-art methods there in doing a black box attack?
Which method? Can you say that again?
Black box style attack. Because you comment on that, the white box attack may not be realistic because they may not release their decoder, right? So what's the state of art in terms of doing the black box attack?
What's the state of the art?
Yes.
So our work is probably early one in this context to attack watermarking based detection. But if we talk about black box attack in general, there are some methods in adversary example setting. I'm not sure whether you are familiar with adversary examples. So adversary examples, basically you have a classifier, you have an image, you add a perturbation to that image, so the classifier misclassifies. Okay. So in that context, people have started the black box attacks a lot. So you have a classifier. This classifier is a black box, and only returns a label for an image input. Now you still want to find the adversary perturbation, right? You want to find the perturbation such that you add to the image, the black box classifier misclassifies. So in that context, people have started some methods, okay? Some methods to find the perturbation. We actually, so if you have time to take a look at our paper, we actually use, our method is actually built on top of some of those methods. Okay, we basically pick a good method in that topic, and we customize it a little bit, adapt it a little bit to the watermark-based detector.
I see. I see. Yeah, I mean, we did some research there. Yes. I'm aware of things like one thing called a square attack. That's probably one of the popular black box attack method. Yeah, yes.
I see.
But
yeah, I use
particularly this domain, you know, for the large language models, I'm not sure whether there's something specific for that. You know, that's basically my question. So.
Oh, that's a very good.
Another literature in the black box attack. Yes, but that's for the general kind of data types.
Yeah, for large language model or text watermarking, I think most text watermarking attacks, to me, maybe I haven't read all the papers because recently there are many, right? So to me, for the paper that I have personally read, I think most of those text watermarking attacks are still common post-processing, using the terminologies I used in my talk, right? Common post-processing like JPEG compression, Gaussian noise, and some strong strategic post-processing. That's where I started. I think for text watermarking, many attacks like paraphrasing, right? Word insertion, word deletion, those are more like a common post-processing. I haven't seen some research that started strategic post-processing to text watermarking, like do this optimization-based attack in the white box setting or some attack in the black box setting.
I see. I see.
Yeah, maybe, I mean, that's based on what I have read. Yeah, but I think that's interesting future work. Yeah. But maybe one reason is that for text watermarking, you do those common post-processing, you can already remove the watermark. So maybe people think there is no need for this severe post-processing. But I think as a research problem, it's interesting. Yeah, it's interesting, like how small perturbation we need in order to remove the text watermark. Yeah.
I see. I see. Thank you.
Yeah, sure.
Thank you, Leo. Due to the time constraint, let's thank the speaker again.
Okay, thank you.
Right. Thank you, guys.
Bye.
Bye.